Okay, let's start. So today we have lecture 7 actually. And we stopped when we were proving the following theorem. This is Levy's characterization of Brownian motion. Let psi of t, where t ranges from 0 to t capital, is a random process such that first psi is progressive, continuous, almost surely, and mathematical expectation minus psi of t with respect to ft. This is exactly the filtration with respect to which it is assumed to be progressive, is 0 for any h greater than 0, any t greater equal or equals greater than or equal to 0. And the fourth condition is the mathematical expectation of the same increments but squared. Conditional f of t is actually h, again for any h greater than 0, for any t greater than or equal to 0. So step 1, we discussed that effectively what we want to prove is that the conditional characteristic function corresponding to h in t is equal to unconditional characteristic function of a Brownian motion. It's going to be sufficient to prove that increments are Gaussian with proper variances and means, and it's going to be sufficient to prove independence. So, and we stopped at step 2. Let us introduce this notation. Ft. And we considered the difference between what we want to have and what we have. And by invoking just standard six, I believe, standard Taylor expansion, we obtain something like this, where alpha is a random variable, with values in 0, 1 in this interval. And step 3 that we announced we didn't finish was devoted to proving the following claim, that mathematical expectation of this expression, which is always defined because it's positive, satisfies this inequality with absolute constant c. And then we can consider this term in this expansion and estimate this as a mathematical expectation to the fourth power ft 3/4. Then it's going to be less than some constant. I remind that c is a universal constant, the value of which can change from line to line, h to the power 3 halves, and it's going to be sufficient for our needs because alpha is the module of alpha is actually less than 1, so we get rid of alpha very easily. we defined for z the following times h n g from 0 to n minus 1. Formally, I need to put n here also. You write t and j, but to simplify notation, I will and is psi t minus psi t j. And then the fourth power of this expression can be written sum j less than k delta j another square. Now let's see what we have here. We got this square plus 4 sum j less sum less than k. This squared times j time L less than j delta L. Now let's consider this term separately. Maybe even we can consider the first two as A1, this is A2, and this is A3. So let's start with A3. This is 4 sum over k delta squared k sum over g sum over L less than g delta k. And I will consider two cases. First case L here. When j equals k and when this does not happen. Then we have sum L less than k delta L. This is this case because the sum is then reduced to one term plus 4k delta squared k sum j, which is not equal to k, L is less than j delta L, and again two cases when L equals k and when L doesn't equal k. This is L, this is k. This gives the first sum. Let's write it down. Now, when L equals k, we get another third power. And then this sum is going to be j greater than k delta j plus j not equal L that is less than j, and we exclude this situation delta j delta L. And we leave the first two terms. This is A1, this is A2. This is I3. Unchanged for a moment. Now, we already showed, previously that for any c greater than 0, probability that the sum of squares which means zero in probability, general speaking, or almost surely along some subsequence. So this means if we look at the expression for the fourth power, we can get rid of a number of expressions here. So here we have the third power and two expressions with third powers. Now, this is almost a telescopic sum, and this is almost a telescopic sum. So it can be bounded by a maximum of Wiener process. So both these sums disappear. If we return to this expression, I1, this is obviously this plus 2 k j less than k, and this goes to 0. So this happens in probability. So passing to a subsequence if we need it, we can assume that this is just a limit of what is left. So what is left? From I1, we get this part. I2 is left unchanged for a moment. So this is k j less than k delta j squared. And what is left from this expression? Only this third term. For some k delta squared k, it should be j not equal to k, and some L is less than j and L not equal k, delta j delta L. The idea is to estimate this expression in terms of something that is guaranteed to be positive. For that, this is already positive, not negative, but positive, surely. Let's consider the sum of this j1 and j2. So sum j1 plus j2, 1/2. I will get rid of 1/2. J less than k delta squared k delta squared g plus 2 sum delta squared k sum j not equal k sum L less than j not equal to k delta j. Well, and I want to make a square here. So let's take the common part outside of the bracket and let's see what we have left. Now, this is almost a square of the following expression. This is less than. Because the difference between this expression and this expression is the sum of squares over j that are greater than k. So it's less than this. So effectively delta psi to the fourth power that's what we get here. J not equal to k delta j squared plus the part that we didn't even touch. delta k delta j squared. So why we did this? Because now we can use a conditional version of the Fatou lemma that allows us to consider such mathematical expectation. So it's less than limit inferior when n goes to infinity. I can put actually limit inferior here too. The mathematical expectation of these two terms ft. Now, if we start to decompose the squares, we will get some constant C1, k, j not equal to k delta squared j plus C2 sum over k jl, all distinct, say, of this form, and plus sum over c k j l and say p delta k delta j delta l delta p ft. Maybe not index, all indexes are present in this sums. Maybe some are excluded when j cannot be equal to k, etc. It doesn't matter. Because obviously, if you are going to calculate conditional expectation of such expressions with respect to the sigma algebra, we are going to use what is stated in the beginning in the formulation of our theorem, and we can see that it's just a mathematical expectation of the first power of any increment conditional on a proper sigma field is going to be 0. So all these terms are going to disappear simply. I will leave this an exercise. We did very similar calculation when we were discussing quadratic variation of the Brownian motion. So this all disappears, and we arrive. This is less than some constant, limit inferior, mathematical expectation of the sum of k, sum over j less than k, delta squared k delta squared j over f t. And again, using the Tower property of conditional expectation, we can immediately conclude that this is like tk plus 1 minus tk, tj plus 1 minus tj. No, this is because of this conditional expectation, we can't do such things, because generally speaking, we don't know where this exists in the terms of whether the expectation of this expression exists. But since we are considering conditional expectation, we always can take those things outside. And this is just limit inferior, sum over k, sum over j less than k, h squared, n squared. So this is obviously and this is the conclusion. Now the last step of the proof is going to be as follows. Let us consider what we wanted initially. And we are going to use the following very simple inequality. A2 plus, should be B1, right? Probably. Now here, A1 is going to be exponent psi t minus psi t n minus 1. A2 is going to be the rest, psi sorry, t plus h. And B1 is going to be which is exactly h over n, is the rest of this part. So it's, and again, the modulus of this and this is less than 1. And now we are going to move backward in time, starting to considering firstly conditional expectation with respect to Tn minus 1, then with respect to Tn minus 2, etc. And in the end, iterating this expression, we will eventually arrive at the following. Here we are going to have k plus 1 minus psi tk minus lambda squared to h over n. The internal condition expectation is going to be with respect tk, and the external conditional expectation is going to be with respect to t. Again, this is very reminiscent of what we already done in this course. And now, using the previous step, but we used it for this expression, now we are going to use this for this. So, using the previous step, we get some constant, the sum, and here we have, instead of h, we have h divided over n, because here delta psi was the increment over the interval of length h, when here it's an increment over the interval of size h divided by n. So it's going to be h divided to 1 to the power 3 halves, and this obviously goes to 0 and then goes to infinity. So we obtained a very interesting characterization of a Wiener process. This is effectively a characterization in terms of martingales, but though we avoid martingales in this course, it's very useful for what we are doing. So last time we already showed that sometimes it is possible to get rid of drift in a stochastic, at least one-dimensional stochastic differential equation, and reduce the studying of this SD to studying stochastic differential equation with no drift. So effect.
Sorry, can you please go over what we proved? So
Here or in the very beginning?
I mean the fourth part.
Here.
Yes, I think. Yes. So what we needed to show is that this
This expression
characteristic
just
function
goes.
is. So can you show the formulation?
Here. So we proved that this is less than something that goes to 0 when n goes to infinity. So these two expressions are just equal.
Okay.
And the difference of this, and this is the estimate for the modulus of the difference of two conditional expectations.
And delta psi is just the increment of the Brownian motion. Yes, I think I saw
Here,
it.
here.
Mm-hmm. Okay.
So we wanted to prove this.
Mm-hmm.
So I put minus, put modulus here, put modulus inside, and prove this is 0.
Mm-hmm. And then we construct, so we divide the interval.
We don't need to divide anything. This is what we wanted to prove. We wanted to prove that this holds.
Yeah, I mean, so we build разбиение, I forgot this word.
Partition.
Yeah, so we build a partition and
Yeah, we use this partition
mhm,
to use the Taylor formula to
yeah.
claim that this difference is small. But for it to be small, we need this difference to be small. And the easiest way to consider small increments in time.
Okay, yeah, so we have the expression which is independent of any partitions, and on the right side we have the estimate with partitions.
In
We can
terms of the size of the partition. Partition is uniform, H is the size of this partition, effectively. So we've proved this independent of n, firstly, and then we say this is holds for any h, so this holds in our case for h divided over n.
Okay, I think it helped. Thank you.
You're welcome. So here we started and just iterate it. Start with this conditional expectation with respect to ftn minus 1, like written here. You will get two terms. The first term, this is forgotten. This is forgotten because it's less than 1. This is exactly this term. Then we have something over a smaller interval from t to t, effectively h minus n, which is tn minus 1. And we now condition over ftn minus 2, we get the second term here, etc., etc.
I see.
Okay, so let's recall. So we started with dig psi of t equals a psi of t dt plus sigma psi of t dwt. And we introduced a new process, f psi of t, and we asked for a condition, what is needed to get t plus. We already discussed the case when we are able to get rid of the drift, and now we're discussing what we can do with this coefficient. Maybe we can simplify the studies of this condition in the sense that this is just 1. So maybe we can do the opposite. Firstly, we got rid of drift. Now we can simplify the stochastic part. Obviously, we cannot get rid of the stochastic part. Sometimes it's possible, but the condition for that was simply this. We'd effectively let. So this transformation transform psi into eta, where eta has a simplified diffusion coefficient. However, there is another way to do this, and this is time change. Time change is supposed to be used in composition with getting rid of drift. So you get rid of drift, and then you think whether it's possible to reduce the studies of a stochastic differential equation with zero drift to studies of just Brownian move. And effectively, this is true. We will consider, obviously, some additional assumptions. Some of them can actually be dropped, and let us introduce the following function. This is infinu over OS such that integral f psi of r dr is less than t. Since f is strictly positive, this is, we can write here just equals. Now, for any t, this is a step in time. And because f is separated from 0, it's almost surely finite. Now, what I want to do, I want to define a new process, but now is psi in new time. So this is often, people talk about this as changing clock your process lives in. So eta of t then sigma psi of r dwr, obviously, just by definition. And what I want to do here, I want to obtain the expression for eta s and sd. So let's consider firstly this integral. Let's call it step 1. Integral from 0 to tau of t, a psi of r dr equals. Now let us introduce a new variable, which is tau of r. Then ds is going to be r dr. Tau is effectively has an inverse function, so it's going to be 1 over the derivative of the inverse function calculated still at this point, dr, and this is going to be f psi tau r. So this is going to be from 0 to a psi from r f. Yep. Though I should have changed s and r here. But then it's integral from 0 to t a divided over f eta of r dr. So this is the simple part. Now we're going to discuss the time change for stochastic integral. Even though it's doable and we are going to do it, maybe not with all the details and under some quite restrictive assumptions, it's a more appropriate way to do time changes for SDEs is actually in terms of martingale problems. But since this is outside of the scope of our course, we will do this here. So the general idea behind this time change in a stochastic integral, sigma psi s dws, is to formally, this is formal, this is not a proof, this is just to write it in the following way. f1/2 eta of r dw tau r. And this is going to be new Wiener process. So let's do this formally. So let us introduce a new process, beta of t, which is defined by this formula. dwr, just there. Now this is a continuous process, and beta is progressive with respect to a new filtration that we introduced at the beginning of our course. Because it's effectively integrals exactly up to these moments. So they're going to be measurable, and they continue, so everything is going to be well measurable. Is going to be 0 again for t greater than s. Because this is going to be the mathematical expectation of the stochastic part minus beta of s, sorry, the increment obviously. And the conditional expectation of this expression squared, again with respect to this sigma algebra, is going by the strong Markov property no, if you do the change of variables in the reverse order, we effectively will divide by f here. So this is just t minus s. So beta is a Brownian motion, but with respect to a new filtration. Which obviously what we wanted to achieve, because this filtration lives in different time. Thus, such integrals that we want to obtain are well defined. Now, what is left to understand why we can change, do this transformation here formal, which is now to be done more properly. So let us consider the next step. I will assume that everything continuous, everything is bounded, etc., etc., additionally to the assumption on f. And that is true for a, etc. And for fixed t, so I'm going to work with this integral for fixed t. Let us introduce such times. This is j t divided over n indicator that this stopping time is greater than this expression, or just this stopping time in case we are already higher than this. So effectively what I am doing, I am considering this interval and doing formal uniform partitioning of this interval. But I need to be careful because tau t can live anywhere here, and I also assume that the definition of tau t in this step incorporates t capital. So we consider everything on a bounded period of time. Then let us consider the discretization of the integral we have, but a new discretization. So instead of discretization with respect to fixed partition, I want to consider this discretization and want to discuss why this is going to converge in L2 towards the integral dws. Now, this is not hard to see. what we effectively want to consider, this is L2 convergence. So we are going to take square roots and take expectations. And again, expectations over disjoint interval will cancel. Cross products will disappear, and we will be left with something like psi n of j minus squared ds. Now, because f is continuous, bounded, and psi is a continuous function, this is going to converge to 0 when n goes to infinity just by the Lebesgue theorem. Lebesgue dominated convergence theorem. We will gather everything into one big integral, and the function that is being integrated is going to converge 0 and is going to be bounded from above. Dominated convergence theorem. So we can believe this result. Let's move forward. I forgot which step it is, it doesn't matter. So I want then to consider one part of this new decomposition, theta nj minus j plus 1 minus w theta nj. And I want to make it look like what we want to obtain. So I want to divide by f, a square root of a, and multiply by the square root of a, f, j, w. And I want to say that this is delta beta in appropriate sense. Now, to say in which sense, note that there are random R and G such that tau R and G equals theta and G. And then this is where this beta should be calculated. So we need to compare this expression this is exactly this, just a reformulation. And this is a proper increment of this new Brownian motion. So we approximate this integral here in a similar manner by using, instead of theta and g, r and g's. And we want to say that our initial integral is the limit of such sums, but these sums behave almost exactly as the sums of this form. And therefore, their limits are going to be the same. Which leads to the following step, where let's have a look at this, the difference of these two expressions. So we effectively have f divided f 1/2 eta theta and j integral from theta and j to theta and j plus 1 f 1/2 theta and j minus f 1/2 psi of s dws. And now taking the sum over all k, this is exactly the difference between two decompositions of our integrals. And since RNG is a random partition of 0t, theta and g was as a collection, a random partition of the interval from 0 to tau t. If we consider the mathematical expectation of this sum minus no, sorry. We already squared. This is going to be mathematical expectation, the sum over k from 0 to n minus 1, integral from n r and g rn j plus 1 f divided f1 half. I'm switching to eta. Now, by the very similar calculation, we arrive at something like this mathematical expectation. G plus 1. This is this term squared, dr. And again, if everything is well defined, we can, for instance, consider any r on this interval, and then eta of r squared indicator that r is exactly on this partition, element of a partition, is again going to converge to 0 because everything is bounded, everything is continuous, and eta RNG and eta R are also continuous. But there is still something to take care of because we need to control the size of this partition. So let's recall that this tau effectively just the inverse functions. So this is going to be infinity and minus 1, and this is going to be where epsilon was the lower bound for f, which means that here we calculated difference between values of eta over the segment whose diameter is controllable. And then we can conclude that eta, we defined it just by time change of a continuous process. This means that it's continuous and uniformly continuous on compact. This means that this goes to converge to 0. Because otherwise, strange things might have happened because for some g, this difference might not be converging to 0. But now we can guarantee that all intervals in this partition are indeed converging to 0. Maybe not uniformly, etc., but they are converging. So the Lebesgue-dominated convergence theorems should essentially work. And now, if we return to the original formulation, we considered a partition of this integral. We considered a partition of the original time change integral. And we more or less showed that the limits of the corresponding expansions are the same. Again, this is not the best setting for such calculation, but still, it's an important result because in the end we can conclude that eta of t is a solution of the corresponding SD with new Wiener process. Now, if we already got rid of drift and f is exactly sigma squared, d at t is just d beta t. So in 1D, any SDE is a Brownian motion after time change and drift removal. This is a very important idea. So as effectively any SDE can be, the studying of any SDE, at least with good coefficients, can be reduced to studying of just a Brownian motion. This leads to extremely deep results in the theory of so-called one-dimensional diffusions of Feller. Moreover, it also gives us some constructive way to prove the existence of solutions. We can start with the Brownian motion, we can do the time change, and we can add drift. Now we are going to continue. We will actually return to this observation in some time. That I think is the very next lecture. Now let's consider the example which unites the Ito formula and stochastic differential equation in the sense how one can use some generalized technique to work with Ito formula and apply it to a function that's not actually twice continuously differentiable. So the function we will be caring for is actually the modulus. We cannot apply just Ito formula to this expression because it's not twice continuously differentiable. But still, studying it and studying some approximation will lead to important insights about SDs and Brownian motion itself. So I will consider the stochastic differential equation with a coefficient that doesn't satisfy standard assumption. Standard assumption with Lipschitz continuity and linear growth. We will get rid of Lipschitz continuity. Signum of psi of t dwt, where signum of x is 1 if x is positive or equal to 0, and -1, minus infinity, 0. The value at 0 actually doesn't matter in the setting. And we will need additional step, which is exactly related to this part. What we are going to prove is known as the Tanaka formula, effectively. So we will introduce C2, now two actually step C2 approximations of modulus. So we can use it formula. Obviously, there are different ways to do this. For instance, people involved in data science can say that the derivative of modulus is effectively the signum, So one can use something from logistic regression and just integrate that function to obtain a good approximation. But we need something that allows us to control also second derivative. We will actually consider one way to do this, and later we'll consider a second method. So let's introduce a new function, f epsilon of x, which is, I think I want to put it slightly lower. Plus x squared to epsilon when our x is less than epsilon. This is almost modulus, but this is a continuously differentiable. Is effectively signum of x when x is greater than epsilon plus x divided over epsilon where x is. So this is C1, but not C2. However, this exists everywhere except for these points. And this derivative is just, this disappears, this is constant. Indicator x less than epsilon. Now let's take a modifier, any modifier you want. So what is a modifier? This is a function, infinitely continuously differentiable, non-negative, that lives in the unit ball around 0 and integrates to 1. And then one can define a sequence of functions f delta x. They are going to converge in weak sense to actually delta function. And now let's introduce our approximation of modulus by f epsilon convolution phi delta. Now then, first, for fixed epsilon, g epsilon delta is going to converge to f epsilon when delta goes to 0 uniformly. Secondly, derivatives are going to converge to this derivative again uniformly. And the third, the second derivative, which always exists because it's a modified version of a function, converge to the second derivative of epsilon uniformly outside any neighborhood. I have no clue how to write neighborhood, so let's assume it's pronounced like this, outside any neighborhood of 0. Now, how to... Right. Sorry?
I think that's right.
Wow. I can say only that. Thanks. I will leave this an exercise, but I will leave you 2 hints. The first hint, if you know what Sobolev derivatives are, then if you have some modifier and some function, say h, then these derivatives go inside of a modification procedure where this is a classical derivative. And this is Sobolev derivative, weak Sobolev derivative. And our f epsilon is exactly twice differentiable in weak sense. This is for any epsilon, the second derivative exists almost everywhere. It's actually piecewise continuous, and this is exactly the weak derivative in the Sobolev sense. This will immediately give you all this statement effectively. Or if you do not know how to do this, you can do this by hands effectively, using integrating by parts, for instance. The first step is effectively something like this: phi epsilon y f delta epsilon x minus y minus f epsilon x dy. So I just wrote this as f epsilon of x integral minus delta to delta phi delta of y dy and substituted. And now this is going to be convergent uniformly in the sense that supremum over all x, supremum over all z of such modulus epsilon x plus z minus f epsilon of x are going to converge to 0. Why? Because f epsilon are very well behaved. We exactly know how they are defined. We know how they behave. We know that effectively everything that happens about these functions happens around 0, and then they behave in a very simple manner. So they just x and minus x, and here they're just constants, etc., etc. So pick the method you want. And let's go to the next step. So this is a modification. This is exactly this. So now we can use the Ito formula. First derivative, ws, dws, plus correction. Correction involves second derivatives, ds. Now, this is going to convert to just modulus. There is no question about this. This is the first observation here. The second observation, so firstly, we go to delta, go to 0 in delta, then we go to 0 in epsilon. Now, the second integral, t g prime ws minus what we want here. We want to obtain its signal ws squared ds. This, when we go in pass to the limit in delta, is going to converge, because everything for fixed epsilon is bounded. This is going to recall that this was almost signal. The difference between f prime epsilon and signum was this part. So this is part that we obtain in the limit that doesn't cancel. So we obtained here, because I'm taking squares, divided epsilon squared indicator s less than epsilon ds. Now this less than 1, because this is exactly the conditions that allows us to get rid of this. So this is just less than 0t. Just probability that ws less than epsilon ds. And this goes to 0 when epsilon goes to 0. So this part is going to converge to the integral from signum in L2. So this stochastic integral is going to converge. Now we are going to take care of all the rest. of the proof. For that, again, epsilon is fixed. Let us define AT is going to be those omega that this expression does not converge in delta to this. Let us recall what was the second derivative of WT. F epsilon was this expression. And we claimed that this happens for all points outside of 0. So this doesn't happen only when W of t equals 0. But integral from 0 to t probability A of s ds. By the Fubini theorem, everything is non-negative, so I can freely switch the order of integration. Indicator, this function, ds. And this is obviously 0, because the probability that ws equals 0 is 0. So, which means that measure, the Lebesgue measure of those s belonging to the interval from 0 to t such that omega is problematic is 0 with probability 1. So with probability 1, with probability 1, almost always when delta goes to 0. Because the Lebesgue measure of those, as this doesn't happen, has Lebesgue measure 0. This is a very typical idea that if you know that something doesn't happen for fixed t and you want something doesn't happen with probability 1 for fixed t and you want to switch that to with probability 1 something doesn't happening for almost all t, you use the Fubini theorem. And as a result, now we can use dominated converter theorem to claim that this happens when delta goes to 0. This means, now returning to the original equation and passing to the limit with respect to now epsilon dws plus, and here we have limit when epsilon goes to 0, integral from 0 to t, the second derivative ws ds. Why I'm writing here limit? Because this exists, so this limit should exist. And it is written in a form that there exists limit when epsilon goes to 0, 1 over 2 epsilon, integral from 0 to t, indicator that ws is less than epsilon ds. And it just equals this expression, dws. This limit is called local time. We are not going to discuss it, but it's a very important way to measure how much time a process spends in the neighborhood of some fixed point, in this case, in the neighborhood of 0. Because if it just considers the situation where it equals 0, obviously it's going to be just 0. It doesn't give any information. But taking such approximation of delta functions, because this is also approximation of delta function 1 over 2 epsilon indicator that x is less than epsilon modulus, we can obtain a trivial process. And this is local time. And this formula is a very well-known result. This is a Tanaka formula. There's a small remark here. So using very similar calculation, we can actually claim that we can use the eta formula in case where a function is almost differentiable. So one can use the eta formula if f is C2 on R except for a fixed number of points. Why? Because the probability that Wiener process hits those points is 0. So they do not affect what happens. In our case, we had a worse situation. We already had problems with the first derivative. But if problems appear only on the stage of the second derivative, that second corrected Lebesgue integral is well defined, it is going to behave in a very nice way. Now, let's return to the original SD. So we asked about signum psi of t, twt. The first observation, so if such psi exists, then psi is a Brownian motion. Why? Because mathematical expectation psi t plus h minus psi of t squared is going to be just mathematical expectation from t plus h signum squared of psi of s ds, but it's just h. And the mean of this process and all conditional means are obviously zeros. So if a solution exists, it's a Brownian motion itself. So let us consider some Brownian motion, which not right now related to this double. Let's forget about that. Let's consider some Brownian motion beta. And let's define a new Wt, but integrating this. Then again, W is a Brownian motion with respect to the filtration of beta, filtration generated of beta, because it's defined in terms of beta. So we again use this Levy theorem, and formally we obtain something like this. D beta t. Now, again, formally, let's rewrite it second time. Beta of t. Wait. What I want to do, I want to do this, I want d beta of t. Let's write it signum squared beta of t, d beta of t. This is just one constant. But now it's signum beta of t, signum beta of t, d beta of t. And this is kind of dwt. So we should expect dwt. Now, this can be made formal in the following sense. Assume we have a process that has a representation in terms of two integrals of this form. For some Brownian motion, doesn't matter. Then we can actually define stochastic integral with respect to these processes. Such processes are called Ito processes. And we can integrate, write something like this. And by definition, we can assume that this is A of S ds plus integral from 0 to t L of S B of S d beta S. And actually, one can construct this whole theory using exactly the same calculation we did for the integrals with respect to Brownian motion by starting with simple function. So assume that alpha is simple, that effectively we have here alpha k indicator that some tk plus 1 of s d beta s, which will lead integrals tk plus 1 s. And now writing this in terms of these integrals, we effectively arrive at something like this. So instead of requiring that just alpha s was square integrable, we now need that alpha s times alpha times a and alpha times b were properly integrable, etc. So this is a formal derivation, but it can be made rigorous essentially very easily. So we can claim beta is a solution of our original is D. The problem with this definition lies in the following. Firstly, minus beta is also a solution because minus signum minus beta of t is just signum beta of t almost surely. It doesn't hold only when beta equals 0, but it happens with probability 1. But we always, in our original construction, started with a Brownian motion, and then we obtained something that is measurable and can be represented as integrals with respect to that Brownian motion. Here we started with beta, and we constructed some Brownian motion W, and we wrote our SDE in terms of that W. So let us recall that by the Tanaka formula, this is signum beta of S d beta S by definition. So this is by the Tanaka formula for beta is actually beta t minus local time for beta. Which means that W is measurable or progressive with respect to sigma algebra G of t, where G of t is generated not by the values of the original Brownian process beta, only by taking modulus first. Because this is a limit, let's recall that local time, it's a limit of such expression. These expressions are also measurable with respect to sigma algebra generated by absolute values of a Wiener process. But that means that beta cannot be progressive or even measurable with respect to sigma algebra, with respect to filtration, generated by W, because information is lost. This contains only symmetrical sets, and this doesn't. This requires another set. So not only we cannot really start with some Brownian process, but we cannot also obtain our solution within the theory we discussed. So if we start with W, then this would hold, because we just said that you can do some switches. And the solution, this beta, is automatically non-measurable with respect to W. This leads to, this is an illustration what happens if you have different types of solution. And at the same time, before moving forward, let's consider the following example. Zero plus infinity psi of t, twt. So this is very similar to what we just discussed. However, in this case, we can construct solution in the sense of the definition we had in the beginning, in the sense that if we define tau, which is infimum over those s that, let's assume that it starts from some x plus w s equals 0, then this psi of t is going to psi 0 x plus plus w t minus tau, which is exactly x plus integral from 0 to t, indicator that tau is greater than s dws. But this is exactly x plus indicator from 0 to t, indicator that x plus ws greater than 0 dws, and this equal x plus integral from 0 to t, indicate just effect indicator the tau psi of s ws, and this is exactly x plus integral from 0 to t signum psi of s dws. So even though these two examples have very similar diffusion coefficients, the behavior of solutions are very different. In the first case, we cannot use the theory we developed to discuss the solution, and yet it exists. In this case, it's covered even though the coefficient is not Lipschitz continuous. So next time, we will very briefly discuss the notion of weak solutions. Why does they exist? What can be said about existence and uniqueness of those solutions, where you can read about them? And effectively, we will also work with some comparison and so-called pathwise uniqueness. And there we will see another standard tool how one can work with functions that are very widely used, such as modulus or maximum 0x, and how one can use the Ito formula to avoid problems with such functions without invoking the theory of local times by very simple technical tools. That's all for today. Does anyone have questions? Okay, I also have a quick announcement, but I will pause the recording for that. It's not important.